Okay, so good morning all of you. Today the next two classes we will focus on the approximate techniques applied to the laminar internal post convection. We have seen the use of these approximate techniques in the case of external flows. Very powerful techniques, we can apply them to flat plate flows without any pressure gradient, as well as the case where we have a pressure gradient. So even for the case of circular cylinder, with when we make use of the Wahl's approximation, so it's a very powerful technique. We can very nicely to a great approximation we can get the profiles of boundary layer thickness, the thermal boundary layer, momentum boundary layer thickness, the thermal boundary layer thickness, and also the expression for Nusselt number which we obtain from using a higher order polynomial is very close to the actual analytical solution. Now, sometimes as close as about 10-15% error. So this integral techniques or the approximate methods are very useful techniques as far as the external boundary layer is concerned. We will see whether such techniques can be applied to internal flows, because in internal flows the main problem, we don't have a very clear boundary layer kind of a flow which we can visualize in an external flow, especially when the flow is in a state where it's about to become fully developed. So there definitely the boundary layer approximations cannot be used. So we can see till what extent we can make use of these techniques in the case of internal flows, and what is the regime where these approximations can be valid. So this is the topic for the next two classes. Before we wrap up the laminar internal flows, so I am going to be talking about the integral method, which is an approximate technique when applied to the boundary layer flows, and we will see how this can be applied to our internal flow problem. Okay. So if you consider say a duct flow, a plain duct flow, that is typically the flow between two parallel plates. Okay, so that is a plain duct. So if you look at the cross section of a plain duct flow, so if you look at the typical cross section, you may be seeing that it is something like this. So you can assume that the width of this plate is some W, and the length of these plates along the x direction is L. Okay, you can see that the width is towards the z direction here. Okay, and then you have your y direction perpendicular to x and z. Alright, so this is a plain duct. A plain duct is nothing but you are not confining it in the z direction, it is just extended to a certain width, and in fact you can also consider that the parallel plate case which you are seeing in 2 dimension is a special case of the plain duct flow, where the width can be assumed unity or sometimes going extending to infinity. So where you don't have any confinement in the lateral directions. Whereas if you have a certain cross section to this, suppose you replace this by a rectangular cross section. Okay, so here you can see the boundary layers may start growing on these lateral walls also, apart from the top and bottom. So then clearly this is not a 2-dimensional flow, this becomes 3-dimensional. Same way with the case of a circular cross section. Okay, the boundary layers start growing simultaneously from all the walls, but in all these cases we have really not looked into the 3-dimensional nature of flow. Whatever we have done so far with the circular cross section was just look at the 2-dimensional approximation of it. Okay, we neglected the radial and the tangential components. Okay, and the radial component was included in the conduction part, of course, but when we looked at the energy balance, okay, we neglected the dependence on the theta direction, the azimuthal direction. So therefore strictly speaking there were 2D axisymmetric what we considered so far. Okay, so this is if you rotate about the axis of symmetry, that's going to give you the 3-dimensional profile. Okay, so that's why they were called as 2D axisymmetric flows. Now this is a 2D axisymmetric flow. However, this is not a 2D axisymmetric flow. This is a clearly 3-dimensional flow. So you cannot rotate it about any axis and get the a profile variation. Okay, so therefore you have to solve this in all the 3 coordinate directions, and the limiting case, the 2-dimensional case of this duct with a finite cross section is your plane duct flow. Okay, so this is where we consider the 2-dimensional approximation of the plane duct flow, where you look at the 2D flow in varying along the x and y direction only without looking at the z direction. Okay, so this is nothing but flow between 2 parallel plates or a plane duct. So there are different names to it, they all mean the same thing, parallel plates. Okay, so whatever we did under internal flows, if you look at the Cartesian coordinate system, they are all essentially plane duct flows or flow between 2 parallel plates. So in such a case, if you look at the boundary layer growth, if you assume that first your velocity boundary layer is fully developed, so you can see that the velocity profile at any axial location will be fully developed profile. Okay, it will be perfectly parabolic. And now if you start heating your plate from a certain location, okay, so either I can maintain a constant wall temperature or flux constant, and you can see that the thermal boundary layer will start developing. Okay, so from here you can take your coordinate system. When you consider thermally developing flows, your x starts from the point where your heating starts. Okay, so from here you find the thermal boundary layer growth happening. So this is your delta T, which is now a function of x. Now at the point when these two merge, then this becomes thermally fully developed. So this is basically your region 3 here, fully developed both hydrodynamically and thermally. This is your region 2, where your velocity profile is fully developed, your thermal boundary layer is developing, and if you go just before several distance axial locations before, you will be in region 1, where the hydrodynamic boundary layer also is still developing. Okay, now the question is where I can apply the momentum integral method. Okay, in which region I can apply. Huh? Yeah. So if you look at region 2, if you have the fully developed velocity profile, then you can focus on region 2 where you have a boundary layer like structure. Okay, so that is only up to a certain distance downstream. If you go further down, you can see somewhere here it loses the boundary layer like structure. The boundary layers, the two boundary layers growing from the top and the bottom walls, they come close and then finally they are about to merge. In such case, your boundary layer approximation will not be accurate. Okay, so you cannot therefore apply your momentum integral or your energy integral approximations in this region, and definitely your boundary layer equations are not valid once they fully merge, because there is no boundary layers, everywhere it is dominated by viscous effects. So a boundary layer, as the definition goes, is a region which is if you look at the total length of the plate compared to that, this is very small, so your delta by L has to be very small, and away from the boundary layer the flow has to be inviscid. Okay, so once the viscous effects start coming, then the definition of your actual boundary layer approximation will not be valid. Okay, so therefore it's clearly, you can see within region 2 it can be applied from the start of the boundary layer to a certain distance downstream. Okay, so these momentum and energy integral approximations can be valid. Same way if you look at the region 1, if you go several distances ahead, so you can find the momentum boundary layer also starts developing here. and once again you can apply the momentum integral equations for the place where the momentum boundary layer is growing. But once it is about to merge, and once it has merged, again the momentum integral equation loses meaning. Okay, so therefore when it comes to using integral method for internal flows, you have to be very careful in which region you are applying. Okay, as far as the momentum integral is concerned, okay, so now you start from your momentum equation. Okay, so you say u du by dx plus v du by dy is equal to minus 1 by rho dp by dx plus nu d square u by dy square. So this is your boundary layer momentum equation, correct, without the viscous dissipation term. Now you integrate this from 0 to delta dy, and you get your momentum integral equation. Okay, so this can be applied for the momentum boundary layer when it is still in a developing state. Okay, so somewhere here you can find that the boundary layer thickness and the boundary layer variation looks somewhat similar to a flat plate case. Okay, so one plate here at the bottom, one plate at the top, but the additional problem that you have is this pressure gradient. Okay, so this makes it a little bit more complicated. So when you have a pressure gradient term, you should know how the free stream velocity is varying. So for example, in the external flow case, you took free stream velocities which are varying of this form. This is the Falkner-Skan kind of a profile. So you should know what is the variation, and then you can substitute for dp by dx as du infinity by dx. But however, in the internal flow case, it is not very clear about this. So therefore one level of approximation would be to directly neglect this, because the pressure gradient terms will not be so much when you look at the initial part of the boundary layer growth. They will become more and more dominant when the two boundary layers start merging, and once it is fully merged, then only the pressure gradient term will balance the viscous terms. The initial terms will not be there. So if you look at the initial part of the boundary layer development, you can make an approximation that this is 0 and this is like now a flat plate flow past a flat plate. The same way that you did the momentum integral there, the same thing can be applied, but this will be a very big crude approximation, and you cannot get an asymptotic solution for the fully developed case from this case, because the momentum integral is not valid for the fully developed case. Okay, so that you should keep in mind. So this is basically the structure of the hydrodynamic development. Okay, it's not very different from your flat plate case, however lot of approximations are involved. Coming to the energy integral, so in the 2D plane duct case, you can of course write your energy equation, which is u dt by dx is equal to, so you can write this as alpha d square t by dy square. We are neglecting the axial conduction term in comparison to the radial conduction, and also we are neglecting of course the radial velocities here. Okay, so these are some approximations with which we are writing the energy equation. Okay, we wrote this for the case where we have a thermally developing region. Okay, so this is the energy equation for thermally developing region or thermal entry length region in the Cartesian coordinate system. Okay, so in the classes we were doing this for cylindrical coordinate system for the case of circular duct. So right now what I am doing is we are looking at only Cartesian coordinate system, that is for plane ducts. Okay. So in that case you can integrate this, and you can integrate that from 0 to delta t, and once again this is very similar to your flat plate energy equation. In fact, even much simpler than that. You do not have your v dt by dx, v dt by dy, so that becomes much easier to handle rather than the flat plate case. Okay. So if you look at the energy integral as such, if you know the fully developed velocity profile, okay, which you already know from your analytical solution, that can be substituted here, and then you can directly use the integral method for calculating the temperature profile. Okay. So this is perfectly valid as far as the thermal entry length is concerned, and once again you should be careful that you cannot reach the solution of region 3, that is the fully developed, thermally fully developed region, as an asymptotic solution to the integral method, because this is not valid in that particular region. The energy integral is not valid in that particular region. So this is what we can say about the integral method. Now once it comes to non-Cartesian coordinates, that is the circular coordinate, that is the case of circular duct, then you cannot even apply the energy or the momentum integral there. Why? Because you have a complicated, so you have here u dt by dx is equal to, you have alpha 1 by r d by dr into r dt dr. So now if you are integrating from 0 to delta t dr, so this becomes quite difficult to evaluate. Okay. So you cannot just like that say this is dt by dy at y equal to 0. So this is a function of r, and you have a function of r inside also. So as such this becomes a little bit more cumbersome to apply this to a circular cross section. Okay. So therefore most of the solutions with using the integral technique are restricted to Cartesian coordinate system. So that is typically the plane duct. So when you are looking at two dimensional flow between channel, in a channel, or between parallel plates, you can look at either the, mostly they are valid when you look at the thermal entry length problem, where you already know the velocity profile, but you do not want to go through the rigorous analytical solution for getting the temperature profile. So there we can use the energy integral. Okay. Once again, when it comes to the hydrodynamic development part, there we have to make some approximations, and the profile will be not as accurate. Okay. So most of the textbooks that deal with the integral method with the internal flows, they look mainly at only the thermal entry length, and that too for a 2D problem. Okay. As far as I know, I didn't come across any literature where they have extended this to 3D circular cross section. Okay. So therefore its utility is very much restricted in internal flows. It is not as wide as in external flows, where you used it for almost all the problems where you had a similarity solution. You replace that with a approximate solution, and in fact even more than that for cases where you had an unheated starting length, for example. So there you cannot use the solution from similarity variables. And again the cases where you talked about with the pressure gradient were much simpler, and also the case where you had a non-uniform wall temperature or wall heat flux. So you had a linear variation or some other variation, any variation. So those were dealt with the approximate methods, but here because of the geometry constraint, so we are fixed to only two-dimensional flows, and also the fact that it is valid only in the region close to the thermal entry length. Okay. And you cannot reach an asymptotic solution to the fully developed case from this solution. So this you have to be very clear about. Okay. Apart from that, the solution method is very similar to what we did with the external flows, only we will have a difference in the variables that we use. Okay. So any questions on this? So therefore what we will now do is assume that we have a fully developed velocity profile and start with our energy equation and look into the thermal entry length, okay, and get the temperature profiles and the expression for the Nusselt number. Alright. So we will have a coordinate system where we will start from here, and at the center of the duct I will use the coordinate system y prime and x. So the one which is starting from the bottom plate I will call the coordinate system as y, and the one which is starting from the center of the plate I will call this as y prime. And from the center of the plate, so this is at a distance of plus d and this is of distance of minus d, this is the location. So the total height of this separation between the two plates is 2d. Okay, so this is basically my coordinate system. So what I am going to do is first I am going to solve for the case of constant wall flux boundary condition, okay, and then the constant wall temperature is very similar and you can extend it. So I am going to look at uniform and now when I define my non-dimensional variables, whether I use Reynolds number or Nusselt number, in the case of plain duct flows it is common to use in terms of the hydraulic diameter or the equivalent diameter. Although it does not have any cross section in the z direction, you can replace your, this is just a spacing between the plates, so you have to write this in terms of the equivalent diameter. Okay, so we will use the definition of hydraulic diameter, okay, which is 4a by p, and if you look at the plain duct, if you imagine the width is very long of course in the z direction, so that is nothing but you have 4 into L times W, okay, so in this case this will be 2d into W, so 2d is this particular, and you have in the z direction W divided by the perimeter. What is the perimeter? 2 into W, okay, so therefore this becomes 4d. So your equivalent diameter, if you talk in terms of some cross section, so you give some representative diameter to that. So similarly you talk in terms of an equivalent diameter, so that is related to 4 times the or 2 times the separation between the plates, okay. So this is your characteristic dimension with which you define non-dimensional variables like Reynolds number and Nusselt number, okay. And we can look at the fully developed parabolic velocity profile. So what we will do is now we will first start with the step and we will integrate it from 0 to the edge of the boundary layer. So we will look at the coordinate system of y when we do this integral, not y prime, okay. So that is why I have written this as dy, so I can express this as d by dx integral 0 to delta t. I can write alpha as k by rho cp, I can take rho cp to the left, rho cpu into t minus ti dy should be equal to integral d square t by dy square. So that is basically k dt by dy between the limits 0 and delta t. So this is at delta t minus k dt dy at 0. So I have just introduced T minus Ti on both the sides because Ti is the inlet temperature. You can assume that the profile which is coming, temperature profile, at x is equal to 0 is uniform, and this temperature is basically Ti. Okay. So there is no harm in just introducing Ti into the derivative. Okay, so now, so this is very similar, and in fact it is simpler than the flat plate case. So there I had a v dt by dy, and I had to rewrite my v in terms of u and convert all my derivatives in terms of derivative with x direction. So now I have directly only a derivative with respect to x direction here, and this is of course related to the wall heat flux, okay, which is known. So what is the value of this? K dt by dy at delta t? 0, okay, that is a boundary layer condition, and minus k dt by dy, this is nothing but your given heat flux, which is a constant. Okay, so therefore in this case your energy integral simplifies to 0 to delta t rho Cp into u okay. So now what do we need to do? So we have the energy integral equation, we will call this as number 1. So this is my energy integral equation. So how do I proceed from here? In the integral methods, where is the approximation? So far there is no approximation made. So this is called an approximate method. Why? Huh? We have to assume a profile now. That is where the approximation comes. We do not know what is the nature of the velocity and the temperature profile. So we have to guess some profile, and I mean the best guess could be something like a cubic profile. As well as the velocity profile is concerned, we are not going to solve the momentum integral because it is now hydrodynamically fully developed. So therefore we cannot guess any velocity profile, but we have to take the exact profile as it is, okay, because if we had guessed a profile then and we applied the momentum integral, that will be valid only in region 1, and that too in the developing section. Once it is close to becoming fully developed, then those profiles are not valid, and we are looking at region 2 now. So therefore we cannot guess anything for velocity, we have to take the exact parabolic profile, okay. So that is basically your u by uc is equal to 1 minus y by d the whole square. I have not derived this, okay, I have derived the velocity profile only for the circular duct, but if you do this for the Cartesian coordinate system, okay, you will get a very similar velocity profile which is like this. So instead of r naught you will now have the half separation distance d coming in the denominator, and this is your centerline velocity, and in your channel case your uc is basically 3 by 2 um, okay, whereas in your circular duct uc was twice um, okay. So I have not derived it in class, but I think already you have done this in fluid mechanics and you should be able to recollect. So this is basically the velocity profile. Now this is written in terms of what? The coordinate system for this is from the center, okay, so therefore this is y prime, okay. So if you look at the profile at y prime of d and minus d, then this will be equal to 0, okay. So that is only possible if the coordinate system is at the center. So therefore we have to now convert the coordinate system from y prime to y, because our energy integral is in y coordinate. So that is because we are operating in a flat plate coordinate system which is attached to the wall, whereas now here it is somewhere in the center of the duct, okay. So how do we do that? What is the transformation here? Huh? So I want a system such a way that when your y prime is equal to 0, then your y should be equal to d, and when your y prime is minus d, your y should be equal to 0. Okay. So therefore your y should be equal to plus d. So when your y prime is equal to 0, y is equal to d, and when your y prime is minus d, y equal to 0. Okay, so this is basically your relation. So you can substitute for this y prime as y minus d into the profile, correct? So therefore this becomes u by 1 minus y by d the whole square by d square, which if you expand you get d square minus y square plus 2yd minus d square by d square, or if you, so this is d square and d minus d square cancels, this can be written as twice of so here again this is d, so twice of y by d minus y by d the whole square. So this is your velocity profile with the y xy coordinate system attached to the bottom plate. Alright, so you can again check. So for y equal to 0, this will be 0, and y equal to 2d. So again, so this becomes 0. So this is 2 into 2, 4 minus 4, 0. Okay, so that satisfies the boundary conditions of the velocity profile. So now once we know the velocity profile, what else? So we have taken the exact analytical solution for velocity profile. So what do we do next? So still we have not done anything approximate here, right? So next we have to approximate the temperature. So here where the approximation comes. So we can assume a cubic temperature profile. Okay, A plus by plus cy square plus dy cube. So this is where you approximate or assume. Now in order to get the coefficients of the polynomial, we need to have how many boundary conditions? 4 boundary conditions. Okay, so what are the boundary conditions? At y equal to 0, dou t by dou y at y equal to 0 should be equal to minus q all by k. This is one boundary condition. And what is the other condition? At y equal to delta t, dt by dy should be 0. So 2 boundary conditions. The third one, okay, so at y equal to 0, if you look at the energy integral, your velocity is 0, therefore d square t by dy square has to be 0, right? So we need one more. And that should be, naturally you can see that it should be at y equal to delta t. Second order should be directly give a second order condition. We have not given condition for the profile temperature itself. We should not go to higher order derivatives without giving boundary condition for the temperature. The first preference is for the temperature. If you don't have that, then you go to the higher order boundary conditions. What will be the value of temperature at y equal to delta T? Ti, right? Because outside the thermal boundary layer, whatever inlet temperature, that will be the same. It is like your flow past a flat plate. You have your T infinity, so outside the boundary layer. So instead of that, you have Ti here. So therefore, you have 4 boundary conditions. So if you substitute these 4 boundary conditions one after the other, you will get all the 4 coefficients, and your final profile will look like this: T minus Ti is equal to okay. So I'll call this as I'll call this velocity profile as number 2, and this is equation number 3. All right. So if you substitute these profiles, this is your cubic temperature profile that you will be getting. So now you have your velocity profile and your approximate temperature profile, which you can directly substitute into the energy integral. So substituting 2 and 3 into energy integral 1, okay. So I can write this as q wall double prime is equal to d by dx, and as far as the velocity profile is concerned, so you have 2 times uc into, of course, uc into 2y by d minus y by d the whole square. I am going to introduce non-dimensional variables here. One I call as eta, which is y by delta t, very similar to the external flow. Okay, you introduced in terms of eta, and you remember you introduced zeta there to denote delta t by delta, right? So here we don't have any delta because we don't talk about boundary layer, momentum boundary layer thickness. So rather than delta, what we should use? D. Okay, you look at the profile, it is y by d, whereas in the external flow it is y by delta. Okay, so there this will be replaced by. So these are the 2 non-dimensional variables, and now you can write them in terms of non-dimensional. So this is rho Cp into uc, and t minus ti is nothing but q wall double prime delta t by 3k. So I can write that as q wall delta t by 3k, which I can pull out of the integral, and now I can integrate from 0 to 1. So instead of delta t, so at y equal to delta t, your eta becomes 1, and you have u into t minus ti, and your u by u have already written as uc into this, so this will be 2 times y by d can be written as eta into zeta. Okay, so this is eta zeta minus eta square zeta square. This is your velocity profile into t minus ti. Already you have taken the constant out, so that will be 2 minus 3 eta plus eta q d eta. Okay, so now you have to simply integrate the resulting equation. So if you what you can do is you can see that for the boundary layer approximation to be valid, your delta T upon delta, that is your zeta, should be small. Okay, just like in your earlier case where your Prandtl number greater than 1, your delta T by delta was small. In your case, for the thermal boundary layer approximation to be valid, your zeta should be small. Okay, so in that you can neglect all the higher order terms of zeta of the order 2 and above. So that means all these is multiplied by zeta square, and this can be completely neglected, and the resulting profile with the first order term can be integrated out, and you should be getting an equation which is d by dx. So when you write in terms of eta here, one more thing, so your y was eta into delta t, so this becomes delta t square. Okay, so this becomes delta t square into, if you integrate it out, you will get a constant times your zeta, because you are integrating with respect to eta. So you will still have this zeta here, that will come out as 15 by 2, and you can take k by rho Cp uc on the other side. Okay, so q wall cancels, of course, is a constant. So this is your equation for your thermal boundary layer thickness. Okay, variation of thermal boundary layer thickness along x. So with this you can now again substitute your delta t in terms of zeta. So this becomes zeta q into d. Okay, so your delta t square, so when you had basically your delta t square, that will be zeta square into d square, and d square is a constant, I can take it to the right hand side. Okay, so I can now integrate it right away, and the resulting profile will be 15 by 2 k by rho Cp uc into d square x plus a constant. Okay, so I can evaluate this constant with the condition that at x is equal to 0, zeta should be what? 0. Okay, so therefore this gives the constant is 0. So therefore my zeta will be 15 by 2 into k by rho Cp uc d square into x, the whole power 1 by 3. Okay, so now what I am going to do is just recast it in a little bit so that I can construct a non-dimensional variable out of this. So my k by rho Cp is alpha, I have uc d by alpha. So I know my relationship uc is basically 3 by 2 um. I can define my Peclet number in this case as um, and what is the diameter I am going to use? My equivalent hydraulic diameter, dh by alpha. Okay, where my is equal to 2 by 3 uc and my dh is equal to 4 times d. Okay, and so I have rho Cp so into d by alpha, that is my Peclet number, and I have another d which I can write as x by d. Okay, so of course I have these multiplication factors which come out. So finally this will come out as 80, the multiplication factors x by dh by Peclet number, the whole power 1/3. Okay, so Peclet number by x by d is nothing but the Graetz number. So you can now directly say that your zeta, which is nothing but your thermal boundary layer thickness, is directly a function of the Graetz number. Okay, so once you get this, the rest of the problem is a little bit straightforward. That is, you have to, so once you got your thermal boundary layer thickness, you can calculate your mean temperature and the wall temperature, and from there you can get an expression for the Nusselt number. So I can calculate my, of course I think I struck off my T minus TL, I will write it again. So this was my temperature profile, cubic temperature profile. Now from here I can calculate T wall minus Ti. So that is at y equal to 0. 2 by 3 q wall double prime delta T by K, right, the other two terms are 0. And I can also calculate my mean temperature, okay, I can so now if you look at this particular expression right here, this is still not complete. We have to get the mean temperature to finally calculate the heat transfer coefficient, because my local heat transfer coefficient is defined as q wall by T wall minus T mean. So I need to get another expression for T mean minus Ti and then subtract both, that will give me T wall minus T mean. So how do I get my Tm minus Ti? How do I get my mean temperature? That is basically integral T minus Ti into u into dy, correct. Now this is the case of Cartesian duct, so your rho u into dy will be the flow rate, so divided by integral u dy. And from the definition of mean velocity you know that um is equal to integral u dy 1 by d, so in this case it is 2d, okay. So I have to integrate to get my mean temperature from 0 to delta T, and I can actually replace this as 1 over d, and my d will be dh by 4, so therefore my um will be 4 by dh integral 0 to delta T into u dy. So that can be, this can be written as um into dh by 4, okay. So now you get an expression where you have 4 by dh and you have u by um here. So u by um I already have an expression, so I also have an expression for T minus Ti, which is this, so I can substitute both of them into this expression and get an expression for Tm minus Ti. So this will be 3 by 2 into 4 into q wall delta T square by 3k into dh, and within the integral 0 to 1 the velocity profile was 2 eta zeta minus eta square zeta square into the temperature profile was 2 minus 3 eta plus eta cube into d eta, okay. So this was your if you integrate it once again, you already did it, but now we are not going to neglect any higher order terms, we will keep that as it is. So your temperature profile Tm minus Ti comes out to be 1 by 2 into q wall double prime dh by k into zeta cube by 10 minus zeta power 4 by 48. Okay, so this I'll this is the relationship for Tm minus Ti. So therefore from this we know T minus T wall minus Ti and Tm minus Ti, we can take the difference between these two and that will give me T wall minus Tm. Okay, so we'll continue on Saturday and complete this. So we can just substitute here and finally you will get an expression for your local heat transfer coefficient as a function of your zeta. Okay, and zeta you already have the expression in terms of the Graetz number. So finally everything you will get in terms of Graetz number. Okay, so these are all just straightforward, you know, you have to just go step by step and you have to do the integration. There is nothing much to explain here, very similar to what we did in the case of the only thing in the internal flows you don't use T infinity, so therefore additionally you need to calculate your mean temperature which is not required in your external flow case. Okay, so we will stop here today and Saturday we will finish the last part of this and we look at the result for the constant wall temperature case also.